Hello.
Yes, sir, you're audible.
Okay, good. Voice audible? Can anyone of you answer?
Yes.
Okay. So as of now, I can see three people over here. A few more may be joining by 7:35. So meanwhile, since there are very few of us, so I would like to know, oh, your name. Your names are already visible, but then where are you from? I mean, what are you doing? Your designation, and why you have taken this course? Okay. So Sadat, would you like to share? Hello.
Hello.
Yeah, please say Sadat. I mean,
Yeah, I'm Sadat. I'm working as junior research fellow in IISc
okay. So you're from ISC. Good. Okay. So in which department are you affiliated with?
in EC.
Okay, see. Okay. So your field of work.
It's on communication, so specifically coding theory.
Okay, information theory.
Yes.
Okay, very good. So you work with all those theoretic bounds and all those heavy math stuff. So others, could you please introduce yourselves? I can see a few more name: Anusha, Shada, Sharalavada, Video. Can you each of you introduce yourselves? Your what are you doing now? Why your reason behind taking this course? Okay, no issues, no issues. So okay, so Santosh, are you able to hear me? Let me know. Okay, you are able to hear me. Fine, that's not an issue. But then, if you have any issues, please let me know because I may not. Okay, yeah, this window will remain open. I will see the. Okay, you are in. Acha, you are an electronic student. Acha, Shalva Singh. Oh, you are from IIT Kharagpur. Yeah, please ask your friends to join as well. Please ask your friends to join as well. Santosh. I'll be teaching something really interesting. Okay, you are from. You are doing MS in GS Sanyal School of Telecommunications. Excellent, excellent. Yeah. So yeah, please do ask other friends to join as well. Although it may this um, will be a recapitulation of DSP. Okay, Professor Subhra Das. I see. You're under Professor Subhra Das. Yeah, please. Okay, so a lot of people are coming in. So let's wait for a few minutes. Mhm. Okay. So it seems there are five of us.
Good evening, sir.
Yeah, good evening. Okay, Anup. So, would you like to introduce yourself? I mean, where are you from? Which course or designation are you in?
Sir, basically, I am pursuing masters from Jamia Millia Islamia in Delhi.
Okay. So,
From yes, MSc in electronics.
MSc Electronics, and what's your specialization?
Sir, MSc electronics.
MSc Electronics. Okay, so
Ye-
it's not something specific like VLSI, RF, image
No,
processing.
no, 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 sir, no.
Okay, okay. So it's
And
a
so currently, sir, I am doing 6 months full-time projects at CSIR Siripilani.
okay, okay. Winning projects. Okay. So what is the motivation behind taking this course?
Sir, I want to make my career in industries, but
Hmm.
after PhD.
Okay, after PhD. Yeah, yeah.
Yes, sir.
Mm-hmm. Yes.
So my aim is to establish my own company.
Okay, okay, very good, very good. Because entrepreneurship is now in a very big flow these days, and especially the ones who do PhDs. I mean, they are in a much more better position to open companies rather than the ones who just do BTechs and MTechs. In fact, at these IITs and in IITs, you might have seen, be it Gandhinagar or wherever, all these IITs, there's a good entrepreneurship culture, and there are really good companies which are being opened by PhD students. Although most of
Yes.
okay. So others, would you like to introduce yourselves? Or can we get should we get started? Lloyd Morris. Okay.
Good evening, sir.
Good evening. So introduce yourselves. Where are you from? Which course are you in?
My name is Lloyd Morris. I am currently pursuing B Engineering in Electronics and Communication Engineering
Okay.
from Mangalore Institute of Technology and Engineering, Mangalore.
Okay, Bangalore. Okay. So you're doing a B Tech BE. Okay.
Yes, sir.
So
B, fourth semester.
okay, you're in fourth semester. Okay.
Yes, sir.
Okay. So what are the courses that you have taken? So in electronics as of now, I mean, have you covered signals and systems?
In third sem, we learned basic signal processing, sir.
Okay, you have already learned basic signal processing. So things
Yes,
like
sir. Yes.
things like FIR filters, IR filters,
Um,
linear phase, they have
no,
been
sir.
okay.
We learned only basics now. This sem, fourth sem, we are learning about FIRs, IIRs, and all.
Okay, okay, okay. So don't worry.
We
I
are
will I will be revising this stuff from bit basic, since it's a 2 hour session and really long session. I will be covering stuff. Okay. So
okay, sir.
it's 7:37, almost 7:40. So is my voice audible now?
Yes, sir. Yes, sir.
Okay, it's audible now. Let me a bit further towards my mouth. Please. Huh. So without further ado, let's get started. So the session is already being recorded. As there are 5 of us. If other people come, we will let them. I'll let them join in. And meanwhile, you can also invite your friends into this session as well. Okay. So hello and good evening, everyone. Myself, Shouharda Ghosh. I am a first-year PhD scholar in the electrical engineering discipline at IIT Gandhinagar. I have completed my dual degree, that is BTech plus MTech, from the microelectronics and my VLSI specialization of electronics and electrical communication engineering department at IIT Kharagpur. So as you know, this is a special PMRF NPTEL TA session. So I will be conducting these sessions every Monday from 7:30 to 9:30 p.m. This, as usual, is a weekly session where I will be solving your previous assignment questions based on the present week's content, and I shall be clearing your doubts. And I may be teaching you something extra that might not be a part of this course content directly, but it will be really helpful to you when you go for designing signal processing architectures. Because let me tell you, I am my area of research is VLSI architectures for signal processing algorithms. So whatever algorithms that we use in our day-to-day life, be it those FFTs, DFTs, or adaptive filters, FIR filters, IR filters are commonly used each and everywhere. You might not have seen them directly, but then they are inevitably present in all the devices. Just as embedded devices are hidden in each and every electronic component, we are not able to see them directly. Similarly, FIR filters, IR filters, and other signal processing toolboxes are actually implemented all over the electronics in all the electronic components that you see in our day-to-day life. So my aim is to introduce to this exciting world and also help you with this NPTEL course. So before we start, I would like to ask you, do you have any doubts regarding the previous session? I mean, in case you have attended this session in the previous week, or you have seen it online in YouTube, I hope it was floated to you, or you have got to know it from one way or the other. Do you have any doubts regarding the previous session? Any suggestions, any questions, any confusion? Okay, so how many of you, I just wanted to get an idea, how many of you have attended the previous session online? Okay, so you attended it online. Okay, and how many, okay, let me lower your hands. Two of you have attended online, and how many of you have attended, not attended, I mean, you have seen this on YouTube, previous sessions? Okay, so you, okay, so Anup, you saw it. Anyways, yeah, fine. Yeah, Anup, you can lower your hand. So it seems almost like only 2 plus 1 3, so 3 of you have already have some experience with this. So if you have any confusions, please let me know, otherwise I will start with today's session.
No, sir, you can start, sir.
Okay, no confusions, very good. So let's get started. Do you see the new slide? Are the slides changing? Am I audible? Are these slides changing?
Yeah, yes, sir, yes, sir.
Okay, they are changing. Okay, they are changing. Good. So I had received an email the previous week that what should be the book that should be followed for this course. So basically, the course is too vast. Actually, it covers a lot of aspects of signal processing, ranging from architecture as well as some nitty-gritties of the signal processing algorithms, and a lot of topic circles, a bit of image processing, a bit of adaptive filters, a bit of FIR, IIR, a bit of architectural optimizations as well. So as of now, apart from the standard DSP textbooks, which I would say are Oppenheim and SK Mitra, I would suggest this book on VLSI Digital Signal Processing Systems by Keshav K. Parhi. It's a very famous book on VLSI architectures and algorithms. So basically, this book actually discusses in a great detail about how to implement these algorithms on full custom or semi-custom design. So when I use the word full custom and semi-custom design, it means that I am talking about VLSI. So basically, how do you use your logic gates, and so you don't get to that detail, but let's say you are building an FIR filter. So every algorithm that you use has fundamentally multipliers, adders, and some other extra stuff. So you're not talking about the extra stuff now, like square root, sine, cosine. They are specially used to use them. But even these multipliers, adders, they're all built of logic gates, right? So how do you build these fundamental units? How do you organize these units of multipliers, adders, and other stuff in order to get a very fast system, high speed system, consume lower power, and use lesser area? Because that's what I told earlier, that our aim is to get high speed, low power, and low area. Okay, so Keshav K. Parhi also has some video lectures. You can search his name on YouTube, and you can see his in University of Minnesota lectures as well. These are classroom. These are not. These are recorded classroom lectures on normal DSP, VLSI for DSP, as well as DSP architectures as well as algorithms. So it would be good if you have a look at his lectures. there's another NPTEL course on the similar topic of VLSI for signal processing that's being offered by Professor Mrityunjay Chakraborty of IIT Kharagpur. I will also suggest you to go to that NPTEL course. I don't know whether it's being offered in this run or not, but yes, it's already recorded, it's already been offered previously, so you can check that course as well. Okay, so yeah, so in the previous week we covered the basics. I talked a lot. Yeah, Anup Pandey, you have raised your hand. Do you have any question?
Yes, sir, only this book is enough.
No, no, no. I would say that this book is not unlimited enough, but at least some of the things that I would be covering today would be based on this. So there is actually no
Okay.
complete book that, and I would suggest you to rather uh, get an online copy rather than buying all the books. Means although buying books are good, but I would say that if you are if you want to really continue, if you want to go deep into VLSI architectures in your research, then only I would suggest you to buy the book, because otherwise there are lots of other topics that you have to cover which are not in this book. I mean, which are not in the purview of architectures and algorithms. So you have be having image processing. There are this course is actually, as I mentioned in the previous week, consists of several small topics touching upon diverse areas. We have image processing, we have FFT, we have DFT, we have other things as well. Okay, so Acha, you raised your hand. Okay, so do you have something else to say?
Oh, no, sorry, sir.
Oh, okay, okay. Oh, no issues. So actually, there is no single book that will touch all of them, and we are not going to cover everything in detail. We have covered to a good detail, but then you know everything that there is no single course that can cover each and everything of the everything that is there being taught in the world. Okay.
Yeah, exactly.
Okay. Yeah. So yeah, you can check the book. It is a very really good one. And then yeah, so previously we talked about the basics of RTSP, what we will be covering in throughout the course, and then we had a great discussion about the number systems. We had good discussion on this fixed point as well as, can you type the book sir once? Okay, let me VLSI digital signal. Okay, so since we are saying that it's storing no value, so 2 0 0 0 0. Okay, and then in the next cycle, if anybody has any doubt, please let me know. If I am hurrying up a bit fast or you're not able to understand anything, please let me know. Then we give a 1, so 1 into 2 is a 2. So initially all of them were 0, so you had 0. So then 2 into 1 is 2, and then this 0 over here gets over here because of the previous clock cycle. 0 over here gets over here. Okay, so all of them are zeros, and here's a 2, so all of them add and you get 2. And now when you again give a 0, then this 1 comes over here, and then this 1 adds with 1 multiplies with 1 to get 1, and rest all of the multiplier outputs are 0, so you get a 1 as an output. And then this 1 which was over here after another clock cycle, it comes over here, and the rest of them, all of them get zeros over here. So the multiplier output in the third one is 3, and rest of them is 0, so all of them add up to 3. So 0 2 1 3 0 0 0 0. So all of them, you can see over here we have got our impulse response 2 1 3. So Santosh, is this clear now? Anup Pandey, Chintu, please let me know if there is. Okay, it's clear. Good, good. So we move forward now. We talked a lot about FIR filter and a good deal of basics of FIR filter. Now it's time to put reassignments. Okay, so our first question of the previous year's assignment is, can FIR filters be derived from analog filters? Those of you who feel that it can be derived from analog filters, raise your hands. Those who feel that it can be derived, means if you feel the answer is true, raise your hands, If you feel the answer is false, don't raise your hands. What do you guess? Okay, so yeah, everybody is right because nobody raised their hands. So basically digital FIR filters cannot be derived from analog filters. What's the reason? Analog filters have finite analog filters do not have finite impulse response. So can anybody tell me the most simple analog FIR filter that you have learnt? Rajashri Tapase, can you please tell me the most simple analog filter that you have encountered in your in any of the coursework? Most simple. You might have even studied this in class 12 as well. Any guesses, anyone? The most simple analog filter you have studied in your coursework? Yeah, low pass a bit okay. Low pass is a broad term because I can say low pass can be this much, high pass can be this one. Diode, diode I wouldn't say diode you are moving to semiconductor. Yeah, Anup Pandey, yeah please.
I think RC filter.
Absolutely correct, RC filter. So basically this RC filter is the first filter that you obtain even in your class 12. Okay, so what is the impulse response when we do it in S domain? It's 1 upon SC R plus 1 upon SC, so 1 by 1 plus S into RC. And when we talk about its impulse response, what's that? Ht equals to e to the power minus t upon RC ut. I hope everything is correct over here. Fine. And how does the impulse response look like? Ht time, so initially it's u of t, so initially it remains 0 and then suddenly there is a spike and decays. Okay, 1. So you can see over here it's an infinitely long sequence. Okay, so you can understand that if the analog version of these analog filters are infinite impulse response. Okay, so similarly if you try to derive FIR filters from them, you will never be able to get the FIR filters. For example, there are Butterworth, Chebyshev, let me check the spelling once. Yeah, Chebyshev. So there are two versions, 1 and 2. Then you have elliptic. So these are the three fundamental analog filters. There are other kinds as well, I am not discussing them, but then these are the three fundamental ones, and all of them are infinite impulse response. Okay, so we can never derive FIR filters from them. They are always used in the IR filter design, which will be studying in the next week. Okay, so our next question is, a general FIR filter has a phase response. I would like everybody to give their answers in the chat box. What do you feel? Is it true or false? Yeah, no responses. Please answer. Is it true or false? Everybody, please type it in the chat box. Okay, so Santosh has written true. Others, please let me know. Yes, so everybody is writing yes. Okay, Sanup has written yes. What about the rest? Acha, yeah, Dr. B. Yeah, Dr. B. Natraja. Would you like to say something, or your opinions on this? Chintu Yadav, Rajshri, Ahwad, your opinions. Okay, so everybody is writing yes. Let's see then what's the answer. So actually sorry, the answer is no. In reality, what happens is that whenever we talk about an FIR filter, let's say I'm talking about a 3-tap FIR filter, let's say h of z is h of 0 plus h of 1 z inverse plus h of 2 z to the power minus 2. Now, the biggest condition for a FIR filter to be general, extremely sorry, to be linear phase is h of n is equal to plus or minus h of m minus n. Now, the most general case means h of 0 is not equal to h of 1 is not equal to h of 2. Okay. So, the general case will never be a linear phase FIR filter. Now, there are various conditions for the various types of linear phase filters. Type 1, let me show the pictures and then I can tell you which one is what. Then you have type 2, then you have, okay, let me make this a bit smaller. Then you have, yeah, so does anyone have any question? I see the hands raised. Type 3, and then type 4. Okay, so what are the distinct features? Type 1 has odd number of, can you convey what do you mean by linear phase filters? Okay, yeah, I will let you know soon. Okay, so as you have already raised that question, so linear phase, okay, so actually I had this question, so let me clear that up directly. So basically what happens is that, it's good that you asked me, whenever you had a transfer function of any filter h of j omega, or let's say h of e to the power j omega for the discrete time case, you can break it up into two parts, the magnitude and the phase. Okay, this is the magnitude and this is the phase. Now, when you look at the phase, okay, phi of omega over omega, I can have a lots of things. Okay, I can have this, I can have this, I may even have something like this. This I am creating from my imagination. There is no guarantee that it will be like this. I am just creating out of creativity. So this is your phase response. Okay, phase response. Now, so what's the linear phase? The linear phase is simply when your phase response is a straight line. Okay, phi of omega, this is some constant, phi of omega will be minus omega n naught. When your phase is simply a negative multiple of the frequency, n naught can be any real number, it's not necessary that it should always be integer. Okay, so that's when that's what you call when this phase is linear. So Santosh, are you clear with what you mean by linear phase filter? Santosh, still a bit. Okay, so you want to understand what is the usefulness of linear phase filters, or still you want to convey the you want to understand the basic one? basic or the usefulness, which one? Basic 2 even, okay. So what happens is that our our every filter or anything has two kinds of responses. One is the magnitude, one is the phase. Okay, the phase actually deals with the delay, that kind of information. Let's say you're given a signal. Let's say I am speaking to you. Okay, I am speaking to you using this microphone. Okay, and there is a very big communication system, and you are able to hear this output. Okay, now I am talking to you at once, let's say at 8 p.m. okay, and you get to hear my voice at 8:02 p.m. so there is a 2-minute delay. Now where does this 2-minute delay come from? Apart from the fact that there is Wi-Fi transmission going on and a lot of other processing stuff, yeah, so basically every system, okay, every processing system through which signals get transmitted has some kind of inherent delay, okay, and that inherent delay is actually captured by our phase. The phase term that you can see over phi of omega, that captures some kind of a delay. So you very well understand that nothing can travel faster than the speed of light. So if I am talking to you at let's say I am speaking to you at 0th second, then you will obviously hear me at after a few milliseconds. Obviously you are not able to hear what I am speaking instantaneously. There is some kind of a millisecond or a microsecond delay because of the Wi-Fi and other routers and other transmission medium involved. So why? It's because all these elements have their own phase response involved, okay. And what happens in the case of linear phase? In case of linear phase, the phase response, the phase is proportional to frequency. And what does that mean? If I look at d phi over d omega, the negative, this is actually called group delay, and it's in naught. So it means whatever frequency of sound I apply, let's say a 50 hertz tone, okay, I would rather say 500 hertz because okay, 500 hertz, you are able to hear it good. So let's say when you talk about a 500 hertz, then it gets shifted by some by a few seconds, okay, and when I give a 1000 hertz signal, it gets delayed by some time, okay. Now let's suppose we are trying to transmit a pulse, okay, x of t or t. You know very well that this pulse will have infinite frequency components, so there are lots of frequencies involved in this. And now when you try to pass it through a system which has a uniform phase delay, what actually happens is that all the frequencies get translated by the same amount of time. You have 50 hertz getting translated by 10 seconds, you have 100 hertz getting translated as by 10 seconds, so you will get exactly the same pulse being translated. But in reality that is not the case. Our systems have generally non-linear response. Sorry, the phase response is generally non-linear. So what happens? I may have 50 hertz traveling at 10 seconds, 100 hertz coming after 9 seconds, 2500 hertz coming after 8 seconds, okay. These are just just random numbers I am saying. What I want to make it clear is that if you say send a stream of pulses, okay, 0, 10, 20, 30, okay. Now we know these pulses are composed of lots of infinite frequency components, and after you pass them to the system, let's say our communication channel, what we will observe is that the different frequency components are actually overlapping. Why is it happening? It is happening because the normal signal over here has which is composed of lots of sinusoids. Now because these sinusoids have different delays, they will no more add up to give you a straight kind of pulse, that rather because of delays you will get some kind of a slewed down waveform which interferes with the other symbols. So this in communication systems, if you have read or if you will be reading in your upcoming semesters, is called inter-symbol interference. Okay, so that's a lot about phase response. So you understand very well the importance of this phase response, that if you have a linear phase response, so your system will not undergo this kind of non-linear phase distortion, which actually causes all your signals to get distorted. Okay, so Santosh, is it clear? Because you are from communication systems, so you should get it very clear. Okay, so it's clear. Good. Okay, so yeah, so there was a term that I mentioned, group delay, which is actually the negative of the derivative of the phase delay. So it was written over here that yn is x of n minus n naught. Its Fourier transform gives you y of omega equals this normal x of omega times the phase shift, and then the corresponding transfer function is this e to the power minus j omega naught. When you take the derivative with respect negative of the derivative with respect to the frequency, you get the group delay. It tells you how by what amount do the different frequencies get deviated. So if your group delay is constant, it means that you don't have any kind of a distortion in your signal. If you have non-zero group delay, sorry, if you have a group delay which depends, which is a function of a frequency, that means that you are in danger, your signal will be distorted. Okay, so now critical path in pipeline processors can be shortened by who can answer this question? Anyone, any idea? Yeah, Anup Pandey, did you watch the lectures?
No, sir, I have no any idea about this.
Okay, so I am explaining this one. Inserting gates. Okay, so Santosh, if you let me clear this first of all. It will the correct answer is actually option 3, inserting latches or registers in between combinational logic circuits. First I will explain you what actually pipelining means, and then I will explain why gates is not the correct answer. Okay, so what happens is that, let's suppose we have this kind of a signal processing operation where you first do multiply, then you do an add. Okay, this is called a multiply accumulate operation. So let's suppose this multiplier takes tm units of time to compute the final product, and this adder takes t amount of time. So let's say I give it I give xn the first sample at 0 seconds. Then can anybody tell me after what time will I get the correct value of yn? At time t, the multiplier takes tm units to compute this product, and the adder takes ta units of time to compute the sum. So how much time would it take to get the output yn? Any idea? Anup Pandey, Chintu Yadav, Ganesh, Shri Rupa, Rajshri. Any ideas? So basically it's very simple. So at time 0 you are getting this xn, a is already available to you at time 0. So after time tm you will get the correct product. Now here it comes at tm, and then vn is already available to you at 0 seconds. So it is at tm, it is at 0. So tm plus ta, so the one that is coming late, that will tell you when you will get the output. Okay, so tm plus ta. So the delay of this path is Tm plus Ta. Okay, this is actually called, okay, no, not this one now. So I hope you have understood the delay is Tm plus Ta. Is it clear to all of you why the delay is Tm plus Ta? Anup Pandey, is it clear to you? Hello, is my voice audible? Can anybody please confirm if I'm audible? Is my video visible? Okay, it's audible. Anup, so is it clear why it's Tm plus Ta? Dr. B. Natraj, could you please tell me if it's clear or not, or is some further clarification needed?
Clear, sir. No problem.
Okay, no problem. Good. Okay, so you understood what? Okay, fine. So you understood why it's Tm plus Ta. Now, let's suppose I have a filter x of n d delay delay. Okay, so you have these filter coefficients over here. Okay, so now you see over here there are lots of paths in this circuit. There are lots of paths. Okay, so by path I mean input to output, which means xn to yn, register to register, which means a block D to a block D, input to register, which means xn to D, and register to output, which means D to yn. Okay, and these paths, remember, between these paths there cannot be any delay element. There can be any other multiplier, adder, any AND gate, NOT gate, anything you can put, but between these paths there should not be any delay. Delay is defined between input, if there is a direct path between input and output, or between any register and another register, or between an input and a register, or between a register and an output. Okay, now what we are supposed to do, we are supposed to find the longest path. Okay, there are lots of paths over here. I am showing over here. This is a path, register to output. This is another path, register to output. This is path, this is not a path, it's nothing is there, it's a path but it's a delay free path. This is another path, this is another path. Okay, so there are lots of paths. So this path is from xn, directly from xn to yn. These paths are from register to yn. Now what happens is that each of these paths have their own delay. Let me name them 1, 2, 3, 4. Okay, so can anybody tell me what is the delay for path 1? Here's a single multiplier and a single multiplier and single adder. What is the path delay for this? Can anybody please confirm? Chanu Pandey, Chintu Yadav.
0, sir.
Why 0? We just did it previously. If you check once, what did I tell you? That here, let's say it can be x.
In starting,
yes, please.
in starting there is no anything, no, sir.
See, in path 1 I have encircled over here. Please everybody refer to this very carefully. The path 1
Sir?
is shown. Hello, yeah, say. Yeah, Chintu.
Pass is not clear, sir.
Okay, okay. Which one? This one or this one? Which one? the xn to yn, y is it tm plus t. Is this clear to you?
Yes, sir.
This is clear. This is clear to you. Okay. So now I said that instead of xn to yn, you can have multiple kinds of paths. You can have xn, some kind of combinational logic. I hope you understand what is combinational logic. Or you can have xn combinational logic and a register D, or you can have combinational logic and a D, or you can have combinational logic and yn. All these four things, all these four types of structures that you can see are called paths. Okay, so first we will see what are the paths in this. Is it clear, Chintu? What do you mean by a path now?
Yes, sir. Yes, sir.
Okay, so now I will show you what are the paths in this. Okay, that will make it more clear. Let me clear it. Okay, so what was our first kind of path? Our first kind of path was xn to yn. Okay, xn to yn, there should
Yes,
be
sir.
no d, there should be just combinational logic. Okay, so this is xn, this is yn. So the first part that you can see over here is this. There is a multiplier, then adder, then you're getting y. Okay, let me encircle this so that you understand what this path is. Did you see this path?
Yes, sir.
Okay, now I will show you another path. dn, delay, xn, sorry, it's not xn, it's a multiplier, sorry, and then you get this. Is this clear? Anup, Roop, Rajshri.
Yes, sir. Yes.
Okay, this is the another path. I am showing yet another path. Delay, multiplier, adder, yn. Is this path clear?
Yes, sir.
Okay, another now final another path is this. Okay, so we have found four paths over there. There were other paths as well, you can see as well. I will show you over here. This is also a path, this is also a path, and this is also a path. So have you seen all the four kinds of path that was that I have shown? I have shown you xn to yn in blue color, then dn to yn in green, another deep blue and another yellow. Okay, and then another path from dn to yn, sorry, dn to yn in yellow, and then dn to dn in these gray colors, and then another xn to d. Okay, all the four paths have been shown. Is it clear to everyone? Anup Pandey, Santosh.
Yes, sir.
Yes, is it
Yes, sir.
clear? Very good. Now we shall see the delay of each of these paths. Okay, delay will be what? Now let me assume over here that the multipliers take tm units of time, okay, to compute their output. Multiplier takes tm amount of time, adder takes ta amount of time. tm, 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 tm. Adders take ta, ta, ta. And when we have to find the delay of a path, we will simply add the delays of the individual elements on this path. Okay, is that clear?
Yes.
No, sir.
Okay,
Yes.
okay, so we are only concerned about those paths, okay, in which there are some combinational elements. For example, there are paths in which from xn to dn over here that I can see, you can see directly there is no element. Okay, you can see this, there is no element over here, it's empty, it's a zero delay path. Okay, there's nothing over here. Understood? So these paths will
Yeah,
not
yes,
consider.
sir.
These things will not consider. So the yellow path that you can see from D to yn, okay, that has one adder and one multiplier. Okay, so that's the delay of path 1. Then you have another one from delay to yn, which has
TM plus
this
2T.
color. Yes, Ganesh.
Yeah, TM plus 2T.
TM
2T plus TM.
2 TM plus TM. Very good, very good. I hope you are now able to catch what I am trying to say. Okay, now the another, the green one.
3TA plus 2A
Very good. 3 TA plus TM.
plus TM.
Okay, and then the final one, xn to yn, it will be excellent, excellent, fantastic. Okay, so there are four as you can see over here, there are four delays in this one. Okay, now in order to ensure that you get a correct value at yn, okay, our clock has a time period t. So what happens is that, okay, I'll clear a doubt. Let me complete before that. So what happens is that, okay, so what happens is that out of all the paths in your circuit, the path with maximum delay is called your critical path. Okay, the path with the maximum delay is called the critical path. Okay, and now the biggest constraint that your system has to face is that your clock period, the frequency, the time period of your clock should be greater than or equal to the critical path delay. The delay of the critical path we denote by T critical, and your clock should be greater than that. Okay, so what does that mean? That means the maximum frequency of your clock is equal to 1 upon T critical. Okay, is this clear to everyone? Because T clock is minimum and to be T critical, your maximum frequency will be 1 upon T critical. Okay, so you understand why our systems do not work at 5 terahertz, 60 terahertz. Okay, there is some critical limitation of the critical path. Okay, so what is the critical path of this filter? Can anyone tell me?
T4.
T4. Very good, very good, fantastic. So this T4, xn to yn. Anup Pandey, Anup, anything to say?
So, the large part that is X to Y,
Yes.
yeah, so this is 4T plus TM, but I think it should be 3TU plus TM. Because it is
Yes. Very good. Excellent. Thank you very much. Thank you. You're very good. So you are absolutely correct. You're absolutely correct. Thank you for pointing this out. It will actually be yeah. We said that, we ended up saying that in a flow. So basically, what is happening is that, why he was saying this is that, yeah. So this one and this one is actually shared. Okay, this is actually a shared one, that's why it will be 3 TM plus T. Okay, so it's 1 TM and then you have 3 adders. Okay, so thanks a lot Anup for pointing this out. Okay, so the critical path of our system will be TM plus T critical will be 3 TM, sorry, 3 TA plus TM. In this yeah, so you can have multiple paths sharing the same critical critical path, same value. Now,
Yes, sir.
unfortunately, what is happening is that we do not want our system to be slow. Okay, so you can see for a there are how many taps? This is a 4-tap filter. Okay, so a 4-tap filter has a critical path of Tm plus 3Ta. So okay, so an n-tap filter will have a critical path of Tm plus n minus 1t. Okay, so you can understand very well that as n increases, my critical path will increase, and what will happen? My maximum frequency of operation will decrease. Isn't that really bad? I mean, when you go to industry or you see modems, so there are like some modems which use around 1000 tap filter. Okay, so when you use higher complexity stuff or higher order filters, then you can understand that's a really bad thing. We can't provide our 1 GB, 6G, 5. We are talking about 5G and 6G, but we cannot provide that performance. So how to deal with that? The most simple solution to this is pipelining. Okay, it's called feed forward pipelining. I am showing you using a small example what we do. So basically what we try to do over here is that we found that our critical path was this one as well as this one. Okay, now we have to break this chain. Okay, this line is creating a very big issue for us. So what we actually do in pipelining is that we create something called a cut set. Okay, so you have these multipliers over here and you have these adders over here. So what we will do, we will virtually create a cut set. So what is a cut set? I will tell you later. So basically we cut the line that separates all these elements, and what we do, along this line we place new registers. Let me clean that up for you and show you what will happen.
It's visible.
Somebody was saying something, please repeat.
Yes, sir. It's visible.
Okay, so yeah, so what happened was that after drawing that line, so wherever we have cut that line, we replace those points by a register. Okay, so now you see what has happened over here. My critical path over here, can anybody see what is the critical path over here now? Any idea? Okay, let me point that out for you. So basically you see the multiplier is alone over here, the multiplier is alone over here, the multiplier is alone over here. Okay, now you see the adders are all over here. So the thing is that actually you won't be able to answer this question because I have not told you anything about the relationship between TM and TA. So there are two kinds of path. Along here you have one path which has TM as the maximum delay and another path which has 3 TS delay. So your critical path will be the maximum among TM and 3 TA. See what has happened over here. Our delay was earlier TM plus 3 TA. Now it got reduced to maximum of TM and 3 TA. Okay, so you can see this reduction in delay. What we have done over here is that if you let me find some FIR filter which was not made very dirty. Okay, let me go to the first one. Yeah, so as you can see over here, okay, you can see this dotted line. So we draw this line and try to separate the elements over here. Okay, and then along these elements we try to place d flip-flops. Okay, this is called feed forward pipeline. Okay, so any doubt till now? Have you understood what is this basic feed forward pipelining and what advantage it has given us?
Yes, sir.
Okay, so actually I won't be discussing this in great detail. There are in order to understand how to do feed forward pipelining or much more detail how to solve these, there are lots of practice problems. So you can refer there are, you can refer to the Keshav K Pari's book, or if you love NPTEL videos, then you can refer to Professor Mrityunjay Chakravarti's course on VLSI for signal processing. He has very nicely explained all about feed forward pipelining, cut set, retiming. Okay, there's a lot of sound coming from somewhere. uh, So you can refer to Professor Mrityunjay Chakraborty's lectures um, on this VLSI for signal processing, where in the first or the second module he explains in detail about how to do feed forward pipelining, and he does not stop there. He continues to talk about IIR filters and how do you pipeline them as well. There are recursive systems. Okay, so for this course, this is much about feed forward pipelining. So basically, what was the advantage? The advantage was that as we insert new delays, our critical path reduces. Okay, so our primary concern over here is to increase the frequency of operation. Now, so has anybody? Yeah, Chintu Yadav, you have any doubt?
So there is an assignment today, sir.
There is a
Assignment.
assignment.
Yes, sir.
There is an assignment. I mean, I didn't get you. I mean, there is an assignment. So, which assignment? NPTEL assignment you're talking about?
This course, sir.
This course is an
Yes, sir.
assignment. Yes, yes. So, do you have any doubt?
Yes, sir.
I mean, see, actually, we won't be able to solve the assignments of the present and ongoing. I mean, ongoing assignments we cannot solve. We've been specifically instructed. We can solve them only after they have been submitted. But can you tell me the concept regarding which you wanted to solve?
IR filter, sir.
Which filter?
IR filter.
IIR filter. IIR filter is not in week 2. Are you sure there's a question on IIR filter? Because IIR filter this week 2 is FIR filter only.
FIR filter, sir. This
Hmm?
week, what is this week assignment, sir?
And what is this week assignment? Yes. Well, actually, yeah. So this week, what I know is that this week you have means at least what I am supposed to teach. I am supposed to teach FIR filters and pipelining and parallel processing. So that's what the agenda, and that's what been posted um, in the portal till now. But if you have any direct issues or any doubts regarding assignment, I would ask you to rather post it in the forum. If you have any doubt regarding any particular concept, please tell me that concept name. I will try to clear that up. But you are saying IIR
No
filter
doubt in concept, sir.
problem solving. So, what kind of a problem can you just tell me once?
No
Because
doubt in concept, sir. Only assignment, sir. How to upload,
um, can you tell me the
how
problem?
to solve assignments.
Can you, Chintu, if you possible, can you share your screen? Means if you do you have the assignment, or you can share your screen once.
I did not wrote any assignment, sir.
Acha, you didn't. Anup Pandey, yeah. Anup Pandey, please say.
Sir, how can I find out this is 4 type filter, this is 10 type filter?
Your voice is
How
not
can I
your
see?
voice is not audible. I mean, can you please say a bit clearly? Figure 5 in week 2
Hello,
is not
sir.
visible. Actually, see,
Hello,
if
sir.
any, yeah, one at a time. So if figure 5 is not visible, I think you should have actually, for this you should have contacted the TAs of the course. I mean, I am not the course TA, I am the PMRF TA. So basically, the logistics of the assignment cannot be, I cannot handle that. You should have mentioned, asked that or mentioned that in the discussion forum. So please put that up in the forum, so I'm sure they will help you with that. Figure 5 in week 2 is not visible. I mean, let me try to open once and check what's the scenario. Okay, I
It's visible, sir.
it's visible. Wait, let me open once. I am trying to see open it from my side. Okay, so I am in the course now. Let me actually log in. I can share you one. Wait, let me. I'm already opening it up. I'll be copying it into my tablet once. Okay, so please hold on for some time. Yeah, so this week 2, I can see quiz week 2. See, we have been told actually not to question 5 x n minus 1. Okay, yeah, it's not quite visible. Whatever I can draw for you is that x of n1 n2 d t there's some adder. Okay, so since it's a present as per the rules, I cannot solve it. But what I can suggest you is that so it's mentioned that was the sampling frequency. Okay, so I will be telling you with the help of the previous example that you have solved over here. Over here you can see this FIR filter over here. So whatever I talked over here over about T clock, okay, replace that by T sampling. Okay, instead of T clock we are talking about T sampling. That is same, that's the sampling rate, the rate at which you are sampling. That's the clock frequency, unless you are talking about it's a nothing much has been mentioned about x of n1 n2. So try to find the so the in that I what the suggestion is that in this in the circuit that they provided in question 5, try to find the critical path. Okay, I've taught you how to find the critical path, the path that has the highest delay. You try to check all the paths over here. Okay, so you try to check the paths that are in the diagram and then check the path which has the highest delay. Okay, I'm sure you will be able to solve this if you try to check the paths, but I cannot solve this assignment now, unfortunately. We are restricted by laws. I can see. Okay, so any other doubt apart from this assignment?
Hello, sir.
Yeah, sir.
So how can we specify this is 4 type filter, this is 1000 type filter?
How do we
How
specify?
can we decide?
Okay. So very good question. Very good question, Anup. How do we specify? So basically, a filter, a FIR filter does not exist in isolation. In reality, what happens is that whenever you design a filter, you design it for some application. So what we do is that before we go on to design any hardware, we do some simulations on MATLAB. Let's
Sir,
suppose
your voice is not audible, sir.
is my voice audible now?
Not clear, sir.
Is it audible now?
Yes, sir.
Okay, it's clear now. Good. So basically what happens is that depending on your application, let's suppose um, let's say you want to do some kind of a low pass filtering for your audio. Okay, you want to do noise very simple crude noise removal. Okay, so what you will do is that you, let's say, okay, fine. So you have this MATLAB FIR toolbox, or you have found some certain frequency specifications that from 0 to say pi by 2. Let me write it over here. Okay, so let's suppose you want to do some kind of a filter, and then let's say from 0 to pi by 5, and then from let's say 4 pi by 5 to pi. This is your pass band, this is your stop band. Okay, so then you try to you give some kind of omega p is your pi by 5, omega s is 4 pi by 5. You give your pass band and stop band ripple. Okay, like let's say this can be one kind of a low pass filter design. These are the specifications as per your application. You give it to the FIR, sorry, MATLAB filter design box toolbox, and then that gives you a set of coefficients. Okay, and that number of set of coefficients is a filter order. Okay, and what happens is that as you try to make your filter stricter and stricter, okay, transition band sharp, high, very high cutoff frequency, very low transition band, the number of taps will be, or the number of filter taps, the filter order will be high. Okay, so it's all application dependent. This I told for a very crude filter. For some other design, let's say an adaptive filter, what will happen is that you initialize, you take an initial estimate, say 100. Okay, and what you do is that you run all your MATLAB simulation, and then check whether the signal whether the performance may be signal to noise ratio, or let's say some other kind of quantity, let's say no mean square deviation, or how close your how much your noise has been eliminated. Lots of things are there, I won't be discussing them. So based on that error metric or that performance metric, you see whether that filter order is working or not. Okay, giving desired performance. Then what do? We slowly and slowly try to decrease the number of taps. Okay, until and unless we reach a point where the performance becomes bad, we stop at that point. We continue going down and then stop at the point when the performance starts to deteriorate. Okay, the point where the performance was just okay before deteriorating, that is the number of filter taps. Okay, in some cases. In some cases you directly give the specification that I just have shown, you can see on your screen, and then that will give the number of taps. Okay, Anup, I hope that's clear. I hope that's clear to others as well.
Yes, sir.
Okay, okay. So I hope everybody understood what this what this pipelining is doing. It's trying to reduce the critical path.
Sir, in this second week assignment, there is one question related to this type of concept. And so, can you see this and how can we
Beta,
specify
okay, okay.
this?
Hold on a second. I mean, are you talking about this kind of formula?
No, 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 sir. In
Are
the second week assignment,
your voice is not
question
clear.
number,
Are you talking about this formula over here? M beta v naught?
no, 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 sir.
Which
No, sir.
which one?
I just talked about the filters, sorry for going technical.
Your
So I just talked
your
about
voice is
this.
not at all audible. Anup, can you please repeat? Can you please type on the chat rather? That would be better. Okay. Meanwhile, if anybody has any other question, please let me know. Chintu, Rajshri, Saranya, Santosh, any question? Okay, Anup, you can try to say once again.
So I can.
Sir, in second week there is question related to filter type, so how can I specify? Are you talking about the
So
one
where we do assignment, sir?
where do you,
We do the assignment, sir.
where is the assignment? I mean, you're asking me, means it's not it's not on my tablet. I'm not showing the
Sir?
assignment. I'm not showing the assignment over here.
Okay, sir.
It means
They
you want.
send assignments to our mail, sir.
Chintu, could you please type it down? Your it's not much audible. I mean, your voice is not clear. So Anup Pandey, you wrote in the second week assignment. There is a question related to filter types. So are you talking about the one that gives a structure and they say low pass, band pass, high pass? Anup, are you saying that?
No, sir. No, no, sir.
Okay, so there was a structure
Sir,
and
can
then
you, sir, can I share my screen?
no, I can't see your screen. Try, where do we do assignment? So Chintu, actually in your NPTEL SWAM portal, actually I'm sure you, when you go over there and then you go to week 1, week 2, when you click on RTSP course, you go to the course and then there will be in the there will be a panel in the left side where you will have something called week 1, week 2. So when you go to week 2 or week 1, any week, then there is an option, there's a drop down box which has the quiz. So what there you have to do the assignment. So Anup, you can share the screen.
Okay, sir.
Okay.
Yes, sir, my screen is visible, sir.
Yeah, I can see your screen. Yeah, I can see your screen is. Okay.
Yes. So this is the question, sir. Question number 7.
Question number
It's visible, sir.
7. Let me check. Let me check from my side. Okay. 7 tap linear phase FIR filter. 4 tap FIR filter. Okay. So,
Sir, how can we specify? Yes, yes.
what is your? Yeah, you can remove it. I've seen the question. So, what was your? Wait. Let me share the screen. Yeah. So, what was your doubt regarding that structure? I saw. Let me draw the, means what is your general doubt? I won't be clear. I means I will be helping you understand the concept behind that. Means you did not understand how to solve this. Anup, are you there?
Yes, sir.
Okay. So
Yes, sir. Yes, sir.
so basically, what I would suggest you is that given the structure, you try to find the. I would try to say that I would rather say that you try to write the equations. For example, let me give you a few rules so that you understand what happens. Actually, I guess since you have not taken the DSP course, this is a bit difficult for you. So whenever you have a delay, you get x of n minus 1. Just see some of these rules that I am writing. Whenever you have a filter, you get a of xn minus 1. Okay. Xn plus yn. Okay. So and then so are these notations clear to you?
Sir, I have a doubt in second one. Why you write x minus 1? Because there is no enough.
What you are having doubt in this one?
Yes, sir, because there is no delay, so why we write xn minus 1?
So sorry. Yes, AX of n. Yes, I copied it directly down here. So is this clear now?
Yeah, yes, sir, yes, sir.
So given these rules, I am sure now you will be able to write the equation of this the filter that you have shown. Okay, and then the number of tabs, as I've shown, as I told earlier, is the number of coefficients. Okay, so over here I told over here it's h0 plus h1 z inverse plus h2 z to the power minus 2 plus h3 z to the power minus 3. This is the 4 tab filter because there are 4 coefficients. Okay, let me check once.
Okay, sir.
There are actually, see, thing is that this is a 4 tab filter. Now tap actually means this. Okay, tap actually means this is a tap. Okay, actually over here there are distinct coefficients, so these distinct coefficients means a tap. Okay, that's a hint that I can give. So something like h0 h1 z inverse plus h0 z to the power minus 2. Okay, this one has only 2 taps because this one is not distinct. You can get this from the h0 itself. Okay, so I hope you will be able to solve now. Does anybody have any other doubts regarding this or any other regarding the assignment? Because we will not be discussing that in too much detail. I can help you solve the concept, but I will not solve that exact problem. Okay, so let's go back. So basically, critical path in pipeline processes can be shortened by insert. As we have seen previously, we had inserted registers in the in between the combination circuit, that was the multiplier as well as the adder. Okay, as you can see over here from the slide also, by inserting latches or registers between combinational logic circuits, the critical path can be shortened. Okay, in the above maximum figure, what is the maximum delay of the circuit? Now here we assume, okay, one thing, I think there is not much data given over here. Let me solve this, give this question in different format. So what is actually happening over here is that whenever we have anything like this, let's say xn a adder yn, what actually happens over here is that we try to represent this as a signal flow graph. Okay, xn a over here d and then b and then y. Okay, so this is the representation over here. Here there is a single node representing some kind of an operation, another node representing some kind of an operation, and over here you have a delay. So now it was asked to find the critical path. So let's see what happens, and let's say each node consumes 1 unit of time. So here it's 1, 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 here it's 1. Now we need to find the T maximum. So to check the path which are the least delay, maximum delay, critical path. Okay, this this is one path, and this is one path, and this is another path. Okay, so there are 3 paths over here. This path has a delay of 2 units, 1 plus 1 2. This also has a delay of 2 units, and this one has a 3 unit delay. So here the critical time over here is 3 units of time. Okay, so now Santosh, if I want to make this a bit faster, what should I do? What should I do over here? If I have to do feed forward pipelining, where should I place it? Okay, so basically what we have to do is that we have to place it along this or this line. So once we do that, we'll have another delay over here, another delay over here. So now what happens? Our minimum path becomes this one, and then Tmax reduces to 2. Okay, so I hope this is clear to everyone. Yeah, so do you have any other doubts, or I can conclude the section here? Okay then, thank you everyone.